5G is on pace to improve many aspects of current generation mobile networks. Some of these major factors include speed, latency, bandwidth, energy consumption, and more. However, in order to do this requires many technologies and communication techniques working together in unison. The first of these technologies, and possibly the most important of all, is millimeter waves. From the inception of mobile networks, all devices have been in the frequency spectrum between 3 kHz to 6 GHz. Now, this wasn't an issue in the past when devices were limited to primarily mobile phones. However, with the emergence of the Internet of Things, self-driving cars, smartwatches, VR, AR, and countless other technologies requiring constant fast connections, these frequency bands are becoming increasingly congested. This rate of growth of connected devices is only set to exponentially increase, with some conservative estimates calling for over 50 billion by 2020. If all these new devices were to remain within the currently established frequency spectrum, no device would be able to get an appropriate amount of bandwidth to operate as designed, which equates to slower operation, dropped connections, and all those other things we just love. Sarcasm. Millimeter waves open up the frequency spectrum from 6 all the way up to 300 GHz, allowing for much more bandwidth to real estate. It's important to keep in mind that we won't immediately use all that frequency spectrum. For the average consumer, it will be more like centimeter waves, with licensed spectrums ranging from 24 up to 40 GHz initially. There will also be a shared spectrum ranging from 60 to 70 GHz plus 4 mission-critical services. Mission-critical services include smart city infrastructure, self-driving cars, healthcare, and more. These services require constant high-speed and low-latency connections. Therefore, shared spectrum is key, and ensuring these devices are always connected. For example, you wouldn't want a self-driving car to drop connection because someone next to you got on a phone call. The shared spectrum is also designed with consumer use in mind. If in your location, the shared spectrum space isn't being accessed and there is a high density of consumer devices, some spectrum space can be allocated for temporary use. Now, you may be wondering why millimeter waves haven't been used as of yet. This is because A, we didn't require them, as there weren't as many mobile and connected devices requiring bandwidth. B, higher frequencies are more easily absorbed by the atmosphere and can also be scattered and absorbed by weather events and buildings. Thus, they require nearly line of sight communication. As such, the technologies required the millimeter waves to become widely adopted weren't previously available. The second primary technology for 5G networks is massive MIMO. It is needed to provide connection for the high density of devices in particular areas. MIMO stands for multiple input, multiple output, and will be applied to our cellular base stations. Currently, MIMO technology is used in a much smaller form, with base stations having between 8 to 12 antennas to handle all the traffic they transmit and receive. Massive MIMO takes this idea and expands on it with the ability to add hundreds of antennas per base station. Just this year, Ericsson started shipping 64 antenna array systems, with multiple companies such as Huawei, ZTE, and even Facebook successfully demonstrating 96 to 128 array systems. The number of antennas per base station is only set to increase as testing and refinement continues. It is expected by 2020, the average consumer will have at least 6 to 8 connected devices, bringing 3 with them wherever they go. If you multiply this single person with the population density of cities, you can begin to see why massive MIMO is so essential in providing all those devices connectivity. Massive MIMO in deployment will be able to provide connectivity to over 1 million devices per square kilometer, which is enough to provide quality connection in the city hubs, stadiums, and other tightly packed areas where current 4G systems often fail or struggle. The main problem with massive MIMO is the interference that all these intersecting waves will create due to how tightly packed together the antennas are. This would result in distorted or destroyed data, which wouldn't be good at all. The next two technologies we'll be discussing are essential in solving the issues millimeter waves and massive MIMO have. Beamforming is an essential data transmission technique required for massive MIMO to work as expected and reduce the signal propagation loss due to the higher frequencies of millimeter waves. Base stations are constantly broadcasting signals, not necessarily aiming for a particular target. When your device receives a transmission from a cell tower, there was a lot of interference produced elsewhere to ensure your signal was received. Beamforming acts like a crossing guard, only sending out signals exactly where and when they are needed by spatially tracking them until they reach their target device. Like Massive MIMO adding more antennas to base stations, there will also be more antennas added to devices as well, ranging from 4 to 16 plus. This addition of antennas is key for beamforming, allowing for more precise advanced spatial tracking. This addition of antennas will allow our devices to connect to the best station in their vicinity to establish a line of sight communication. Taking it one step further, beamforming will be spatially aware enough to bounce signals off obstacles in the environment to ensure they reach their target location. Before we begin discussing the next technology, I want to play this clip from Qualcomm as it shows all the technologies we've discussed thus far working together in unison. So, what our research center did is they took a fixed solution and they added adaptive beamforming to it. So what you can get at millimeter wave is very high gain antennas. So we're looking at many antennas. You might have arrays of 4, 8, or even 16 and many antennas around the device. And on the base station, we're looking at numbers of antennas that could exceed 128, 256, or even higher. Beamforming is all about setting the right amplitude and phase for each of these elements so that collectively they steer the beam in a certain direction. This has to be done dynamically. You think of it as a spotlight on a stage where a performer is on stage and is moving around and the spotlight follows. So when you see our GUI or a UI, you'll see like a spherical design of where the energy would be most attractive in terms of providing the performance we want. So depending on the angle of arrival of the energy, depending on which reflection in the environment is providing the best path, that's what we'll be able to select, and that's part of the beamforming algorithm and the communication between the UE and the base station. Small cells aren't necessarily a new technology, but we'll see greater use with the evolution of mobile networks. Small cells are essentially smaller base stations that can be installed anywhere. They range in size from large macro cells to micro and pico cells that can be installed on top of buildings and street lights, all the way down to femtocells that are often user-installed. Up until recently, small cells have primarily been used to expand coverage to rural areas. However, in combination with 5G technologies will be key in reducing the propagation loss of millimeter waves and routing beam-formed signals. This technology will be essential in ensuring consistent high-speed, low-latency coverage wherever you are. An example of how important and powerful small cells can be when utilized properly is the small cell delivery concept Nokia recently demonstrated. Based off network capacity and need for coverage in a particular area, drones can deploy solar-powered small cells that immediately connect to base stations and provide data. This will allow networks to support seemingly infinite capacity, with autonomous drones taking the cells wherever they are required. To further illustrate the power of small cells, imagine stadiums or concerts. Often these areas have poor connection due to the high volume of people in such a small area. With the power of a Massive MIMO being able to support 1 million devices per square kilometer and multiple small cells in the stadium, everyone can get access to a high-speed connection. This will also enable the ability to change the way live events are streamed to the public. Full duplex is a communications paradigm which can solve the issues that reciprocity creates. The principle of reciprocity in electromagnetism applied to cellular networks essentially states that an electromagnetic wave must transmit and receive on the same frequency. Now this would cause major signal interference, which is why until now, to work around this, we use different frequency bands when transmitting and receiving. The problem with our current solution is that we have to use double the frequency spectrum space when trying to communicate between devices. To solve this problem in a way that could be applied to our devices, engineers have recently created fast silicon switches which allow the signals to essentially travel around each other instantaneously. Full duplex will increase spectral efficiency by a factor of 2, which essentially means that our current frequency spectrum can support double the number of devices. This technology is very powerful because not only it be applied to 5th generation mobile devices, but newer 4G devices as well. Now, as I stated earlier, the technologies will improve upon many aspects of current generation technology, but we'll focus on 4: speed, latency, bandwidth, and energy consumption. Let's start with speed. The standards to define the speed of a 5th generation mobile network are at 10 gigabits per second, translating to a 100-fold increased from current maximum speeds. However, many tests for 5G are constantly working on pushing this boundary even further.